All right, so in section 1.5, we're going to be talking about the limit of a function. So the first way that we kind of approach this is we use an intuitive approach to actually understanding what limits actually do for us. So suppose f of x is defined when x is near a number a. Then we write the limit as x approaches a of f of x equals L. If we make the values of f of x arbitrarily close to L by restricting x to be sufficiently close to a, but not equal to a, then what we can say is a limit exists. So let me explain what I mean here. And I think this is a really good example of kind of demonstrating what limits do for us. So I want us to go ahead and graph f of x equals x to the second minus x minus 6 all over x minus 3. And I'd like us to evaluate f of 3. And then I want us to look at and explore what does this mean, the limit as x approaches 3 of f of x. So I went ahead and did this in Desmos. So I'm just going to come over to here. Let me get my mouse out real fast if I can find it. There it is. All right, and here's what this function looks like when I graph it. Okay? Now, as you can see, this kind of looks like a straight line. All right? But hopefully, some of you out there are looking at this and going, well, wait a minute. There's some issues that arise. First and foremost, the first thing I want you to do is evaluate f of 3. So let's go back to our notes. And what you should notice here is that when I evaluate f of 3, so let me write this out real fast. And I substitute in my 3. I'm not even going to worry about the numerator because instantly I see in my denominator, I get a 0. And anytime I have a number or a value divided by 0, we call that undefined, okay? Now, that means there's like no solution, correct? However, if we go back and we look at Desmos real fast, if you look at the value of 3, which is right here, hopefully you can see my mouse, all right? So if we look at 3 and we come straight up, well, it looks like the output is equal to 5. So you would expect the answer to be when x equals 3, f of x equals 5. But algebraically, clearly that doesn't work. So we need to ask ourselves, well, what's happening here? Are we wrong or is the calculator wrong? And in reality, I'd have to say neither of us are wrong. It's just the way that we interpret this, okay? So let's go back and I'm going to go ahead and copy and paste this into our notes. So just give me 1 second here, because I really want us to evaluate this second part here. All right, so that is rather large. There we go. All right, so the second thing I wanted you to do is I wanted you to evaluate the limit as x approaches 3 of f of x. And I want to figure out what that is equal to. So here's what limits allow us to do, okay? Right there is the value x equals 3, okay? And when we say the limit as x approaches 3, what we're saying is, what if we were to go on the x-axis here? And what if we were to walk? And it doesn't matter what side. What if we were to walk on either side of the number 3 and get closer and closer to 3? And what I mean by closer and closer to 3, like on the left, we could have values such as like 2.9, 2.99, 2.999, and those values of x are getting closer and closer to 3. Now, we know if we were standing at exactly x equals 3, we get a function that is undefined. However, what if we're right before it? Or what if we were on the opposite side of it? So let me do 3.1, 3.01, 3.001. Notice I'm not at 3, but I'm right next to it. And I can keep making these values on the left-hand side get arbitrarily closer and closer and closer to x. My question would be, well, if these get closer and closer and closer to 3, what are my f of x, or if you want to think about it, what are my y values approaching? Okay? So an easy way to kind of think about this, and like I said, this is our intuitive approach, would be, all right, well, let's take the case that we are on the left-hand side of 3. So we are walking this way closer and closer to 3. And if I just take my head and I look straight up, notice my y values are getting closer and closer and closer to this value of 5. All right, they're not exactly 5, but they're getting closer and closer and closer to 5. All right, and then the same exact thing approaches, or the same exact thing happens when we approach 3 from the opposite side. So if I just look up, notice that although I'm getting closer and closer to 3 from the right-hand side, my y values are still approaching whatever this y value happens to be, which it looks like it's going to be the number 5. So what we would say is the limit as x approaches 3 of f of x equals 5. Okay? So it doesn't mean that we're exactly at 3. Limits allow us to be infinitely close to 3 without actually being at 3 itself. All right? All right, now just to convince us that the answer is actually 5, okay, I went ahead, paused the video, and I'm going to create like a little Excel spreadsheet. So in the first 2 columns, I have x on the left-hand side, and then f of x is approaching. And then over here on the far right side, it's going to say x on the right-hand side, so I'm approaching from the right-hand side, and f of x is approaching what values there. Now, currently, I have, for the x left and the x right, x equals 3, which we know is undefined. In fact, Excel is actually telling us cannot divide by 0, all right? But now what we're going to do is we're going to pick numbers of x that are going to be closer and closer and closer to 3, but on the left-hand side of 3. So remember, I had 2.9. Oh, let me make sure I type it in the correct cell. So I got 2.9. And notice that the answer is 4.9, which is relatively close to 5. How about 2.99? Let me just kind of do that real quick. How about 2.999? How about and I'm just getting closer and closer and closer. And as you can see here, my answers, my f of x is approaching the value of 5. Okay? Now we're going to do numbers on the right-hand side of 3. So how about 3.1? All right, and notice that it's 5.1, okay? So I'm going to go down just a couple cells here and copy down the formula. How about 3.01? And then 3.001? And 3.0001. And notice that all these values are starting to approach the value of 5. They're getting infinitely closer. So since the values on my left-hand side and the values on my right-hand side are essentially the same number, remember, I can keep getting infinitely closer and closer and closer to 3. My f of x values are getting infinitely closer to the value of 5. And this is what we call the intuitive approach to finding limits. Is we just kind of, if you want to, and I would highly recommend graphing and then using your intuition and reading the graph on the left and the right hand sides to see if they're approaching the same exact value. So now if we go back to Desmos, ideally this graph should look like this. And this is one of the major disadvantages with using a calculator, because sometimes calculators can lie to you. And in reality, there's a hole at 3, 5. And this is what the graph of x to the second minus x minus 6 over x minus 3 should look like. All right? And with limits, you can convince yourself now that there is a hole there. Because we know at x equals 3, we cannot evaluate that. However, the limit of x as x approaches 3 of f of x is going to equal 5. Now, I will say this. Graphing is an extremely powerful tool that we can use, but sometimes we do got to be careful, all right? So let me show you an example of where we need to be careful here, all right? So we're going to go ahead, and I'm just going to kind of reset this real fast. I guess this will work. We're going to graph this function right here. All right, it's going to be the sine of pi over x. Okay, so graphing is a really powerful tool, but we do got to be careful because sometimes it actually can harm us tremendously. So let me give you an example of what I'm talking about here. So we're going to go back to Desmos, and here's another graph. Now, this is the graph sine of pi over x. And already you can see something really bad is happening. In fact, if I were just to keep zooming in and zooming in and zooming in, it seems as if the closer and closer and closer I get to 0, the more and more and more that this function oscillates in between -1 and 1. In fact, it's really hard for me to even zoom out. All right, so let me go ahead and let me copy and paste this into our notes. All right, and then here's the problem. What if I ask you to evaluate the limit as x approaches 0 of f of x, where f of x is going to equal the sine of pi over x? Well, clearly you could see the issue here. This oscillates uncontrollably the closer and closer and closer you get to 0. Okay? So then we need to think of another way to do this. Okay? So graphically, very powerful tool. Here it fails. But we just kind of convinced ourselves in a previous problem of another technique, which is using Excel, or go ahead and picking arbitrary values that are really, really close to 0. So let's go ahead and let's do that. So I'm going to pause the video, get this set up, and then I'm going to come right back. Okay, I am back here. So I went ahead, typed everything into Excel. All right, and here's what's happening here. Notice on the left-hand side, if we're on the left-hand side of 0 and we get infinitely closer to 0, we get these values right here. 0.0159, 0.0158, 0.99, then all of a sudden it's negative 0.216, and then 0.816, and so forth. If you compare these values with the values of when we approach 0 from the right-hand side, notice that not only are they basically the same values, but they're the exact opposite signs. If you look here in this first row, all right, even though we are an equal distance away from 0 on either side, they're approaching two completely different values. One is positive, one is negative. The same occurs in the second row. One is positive, one is negative. Even in the fifth row, all the way down here that I'm highlighting, notice it's negative 2.168, but if we're on the right-hand side, it's positive 2.168. All right? So here's what we can conclude. And I'm going to just write like a little sentence out here. In fact, let me go ahead. Let me go back to Excel because I want to copy and paste that into our notes. All right, so we're just going to create like a little window here. We're going to copy and paste this into our notes, kind of as like evidence. And what we're going to say is this. Since our values of f of x do not approach the same number, and we'll call that number L, we can conclude that our limit as x approaches 0 of sine of pi over x does not exist. Okay? So sometimes limits just don't exist. And I think I've hopefully demonstrated with two really powerful situations here, where in the first one, we have a limit that does exist, and in the second one, we have a limit that does not exist. And we also demonstrated this in two completely different ways, which is really, really powerful for us. powerful for us because you can determine limits using a graph, or you can do it numerically. That's using a table. And we also did it in the second example the same way. We used the graph and then we demonstrated that the limit does not exist numerically. It's just with the second example, using a graph was very, very difficult to do. Instead, you can obviously use a numerical approach to kind of convince yourself. And here's the best part about this. There's another way that you can compute limits and determine if they exist or not. And if they do exist, where are they approaching? And we can do that our favorite way. We could do this algebraically. And that is going to be in the next section. So what I want to do now is kind of really dig down deep into limits in general, because if you noticed here in this first example, the very first example, let me scroll all the way up. Notice I asked for the limit as x approaches 3 of f of x. And then the way I described it was, well, you were approaching from the left side, and then you were approaching from the right side. And we found that this limit equaled 5. Then we did the same exact thing. I asked you to evaluate the limit of f of x, where f of x equals sine of pi over x. But notice we are still approaching from the left side and from the right side. What I want us to do now is I want us to understand and explore the idea of one-sided limits. And it's exactly what it sounds like, okay? So the easiest way that sometimes we demonstrate this is using the Heaviside function. So the Heaviside function is a piecewise defined function that looks like this. So we say h of t equals the piecewise defined function of 0 if t is less than 0, and 1 if t is greater than or equal to 0. And graphically, that looks like this. Here's t, here's h of t, and our Heaviside function, and I'll write it in red so we can really see it, is 0 if t is less than 0. So it's an open dot, and then we would just shade the x-axis going this way. And then it's 1, and you can include 1 because we have the greater than or equal to, as long as t is greater than or equal to 0. All right? Now, here's a really good understanding of what's happening here. First, notice this right here is called a jump discontinuity. All right? In other words, there is no way that you can graph this Heaviside function without physically lifting up your pencil to do that. Therefore, we call this a jump discontinuity. Now, if I were to ask you to evaluate the limit as t approaches 0 of our Heaviside function, then hopefully you can see that, and I'm going to get my black marker out again. Hopefully you can see that if I approach 0 from the left-hand side, and then I approach 0 from the right-hand side, they are not approaching the same number. In other words, and this is so hard for me to demonstrate in like a video, in a YouTube video, because you can't like see my hands. But what I want you to do, if you can, and hopefully I can describe this clearly enough, is put your left finger, your left pointer finger, on the x-axis on the left-hand side of 0, and then put your right pointer finger on the right-hand side on the top line of the Heaviside function, and then allow your fingers to get closer and closer and closer to the value of x, or t equals 0. And you're going to notice that your fingers will never ever touch. And since your fingers never ever touch, what we can say is that the limit as t approaches 0 of the Heaviside function does not exist. And it's because you are not approaching the same output. However, I can give you this example here and say, well, what is the limit of this? And let me write it first. And I'm going to tell you what the answer is. Okay? And I'm going to read this to you. So this is called the limit as t approaches 0 from the left. So this it looks like an exponent. It's a minus sign. All that is, that's notation for from the left. That's all it means. And also, on the flip side of this, you could say, well, t approaches 0 with a plus sign in the exponent, and we say that t approaches 0 from the right-hand side of h of t, and hopefully from the right-hand side, you can see that the answer is 1. And now, what we can do is really define what a limit is using one-sided limit. So let me go ahead and let me copy and paste this into our notes. Okay, I'm back, and here is our theorem number 3, and this is quite possibly one of the most important theorems when it comes to identifying limits and whether or not they exist. What we will say is the limit as x approaches a of f of x equals L if and only if the limit as x approaches a from the left of f of x equals L and the limit as x approaches a from the right of f of x equals L. In other words, these two limits right here, the limit as x approaches a from the left of f of x has to equal the limit as x approaches a from the right of f of x. And if this is true, so if these two things are true, then the limit as x approaches a is going to equal L. And a really good example of what this looks like in action is the very first example that we did. So if I just go ahead and scroll all the way back up, okay, so here's that example right here. So what I could have really asked you at the very start of this here is I could have asked 3 questions right from the very start. Sorry, I hit a button on my keyboard and it screwed me all up. Anyways, here are the 3 questions that I could have asked you at the very start of this. And I'm going to write it in this little gap all the way up the top of your screen, upper left-hand corner. The first question I could have asked was, what's the limit as x approaches 3 from the left of f of x? Well, as x approaches 3 from the left, our outputs are approaching 5. Then the second question I could have asked was, what's the limit as x approaches 3 from the right of f of x? Well, that would be the exact opposite side. I'm approaching 3 from the right-hand side, and notice that my outputs or my y values are approaching 5 again. And finally, what's the limit as x approaches 3? And when we just write the number 3, all right, so let me erase this real fast. I just want to write it cleaner. So if I write the limit as x approaches 3 of f of x, whenever you see it written like this, and I'm going to highlight it for us, what this is really telling us is we are approaching from both sides. Okay? That's what we're really asking. And since the left and the right are approaching the same exact value, then I know not only does the limit exist, but it approaches that value that the left and the right side limits approached as well. All right, so the last thing that I want to go over in this section is just one more type of limit, and it's called, oops, if I could spell, that'd be fantastic. Infinite limits. And they're not they are not scary at all. In fact, I'm just going to use the example in the book because it's one of the best examples that exist. So let me go ahead back to Desmos. Let me get rid of this. And I'm going to go ahead and graph 1 over x to the second power. Okay? So this is what the function 1 over x to the second power looks like. And I'm going to go ahead and just copy and paste this into our notes again. All right. And we're going to explore this using our concepts of limits and both approaching from both sides and then the left and the right. In fact, let's do the left and the right first. So if I ask what's the limit as x approaches 0 from the left-hand side of 1 over x squared, well, you're approaching 0 from the left, and notice that this grows without bound. Like, it doesn't really approach a value because it just gets closer and closer and closer to the y-axis, which is, ironically, it's a vertical asymptote here. So we would say that this limit equals infinity because it just keeps getting larger and larger and larger. Okay, this is going to keep getting bigger and bigger and bigger. Now, if I asked, well, what's the limit as x approaches 0 from the right of 1 over x squared? Well, we're approaching 0 from the right, so this is going to grow once again without bound. So we would say it's positive infinity again. And finally, if I ask for the limit as x approaches 0 of 1 over x squared, remember, this notation is saying you are approaching from both sides. And since both sides approach the same exact value, in this case, infinity, then this is going to equal infinity as well. All right? And that's as hard as it gets. Like I said, it's not that scary. Okay? But, you know, sometimes you do got to be careful. Okay? So let me show an example of where we do have to be careful. So we're going to go back into Desmos. And I'm just going to change one thing here. And instead of it being 1 over x squared, I'm just going to make it 1 over x. So we call this the reciprocal function. So let's go ahead and copy and paste this into our notes. There we go. And once again, we're going to ask the same three questions. What's the limit as x approaches 0 from the left of 1 over x? Well, that's going to be negative infinity because it's going down this way. Okay? What's the limit as x approaches 0 on the right-hand side of 1 over x? Well, we're going to say that's going to be positive infinity. And I'm going to write the positive in front of it just to really drive home, the point here. And then finally, the limit as x approaches 0 of 1 over x does not exist. And the reason for that, on the left-hand side, we're approaching negative infinity. And on the right-hand side, we're approaching positive infinity. And since the limit as x approaches 0 from the left of 1 over x squared does not equal the limit as x approaches 0 from the right. 1 over x. Not 1 over x squared, 1 over x. Since the limit does not equal the right-hand side limit, we know it doesn't exist. And that is our proof right there. So the last thing I want to do is just kind of do an example that kind of summarizes everything that we're talking about here. All right, so let me go ahead and just copy and paste this. So there we go. Here's a nice little graph. All right, it's not exactly the prettiest thing, but it'll work. All right, and what I'm going to do is we're just going to answer a bunch of questions here. Okay, so what is the limit as t approaches 0 from the left of g of t? So we're going to call this entire function g of t. So this is going to equal, now if I'm approaching 0 from the left, that's going to be over here. And my limit is going to be this value right here, which is going to be negative 1. Okay? Now, the limit as t approaches 0 from the right of g of t. Well, now I'm approaching 0 from the right, so from the right, and it's actually coming down all the way down here. And that looks like it's going to be negative 2. So then finally, what is the limit as t approaches 0 of g of t? Well, that's going to be does not exist, and that's because the left and the right-hand sides do not equal each other. Okay? Now, the next question would be, all right, well, what is g of 0? G of 0 equals negative 1. So let's not get confused with this, okay? The first three questions, I'll label them A, B, and C respectively, are all limit questions. So you're not actually at the value of 0. You are approaching the value of 0. Part D is literally asking you, if you evaluate this function at t equals 0, what is the output? And in this case, it's right here. It's the solid dot at at g of t equals negative 1, okay? So you got to be really careful with this, all right? Let's go ahead and let's look at a couple more examples. All right, all I did was just erase. So let's go ahead and let's look at What is the limit as x approaches 2 from the left of g of t? Well, approaching from the left, here's my outputs right here, so it looks like it's approaching 2. What is the limit as x approaches 2 from the right of g of t? Well, if I'm approaching from the right-hand side, looks like my values are coming down here, so that's going to be 0. And finally, what is the limit as x approaches 2 of g of t? Well, since the left and the right do not equal each other, once again, we say it does not exist. And then finally, if I ask you to evaluate g of 2, well, that answer is going to be 1. And that's because of the solid dot right there in the middle. It's defined at or t equals 2, and what is that output? It's going to be the value of 1. Okay? So that's it for this lecture video. I hope it clarified what limits are. In the next video, we're going to be talking about how do we evaluate limits algebraically. And we have, I think it's like 5 or 6 limit laws that actually, that will allow us to do that. So I will see you in the next video.